This evening, we're going to explore the outer boundaries of our solar system, reaching toward Neptune, the farthest planet we've ever named as our own, sitting out there in the dark about 2.8 billion miles from the Sun. And we're going to determine what it would genuinely demand to get there. Not just the engineering or the physics, but the reality of what such a journey would mean for the humans who attempted it. Because here's the thing most people don't realize. Getting to Neptune isn't just hard. It isn't just a matter of building a more powerful rocket or waiting another decade for better technology. It's something far more extreme than that. The first humans to reach Neptune would almost certainly never see Earth again. Not because something would go wrong, not because of a disaster or a catastrophe, but because of physics. This was because of time, because of what the human body and the human mind can actually endure across the kind of distances we're talking about tonight. Yet this question persists in the imagination of engineers, scientists, and dreamers. We keep asking it not because the answer is encouraging, but because Neptune represents something fundamental about human ambition. It sits at the boundary of what we can theoretically achieve versus what we can realistically accomplish. Understanding this boundary teaches us something crucial about the limits of our species and the universe we inhabit. Think about what that means for a moment. We're not asking whether we have the courage to make this journey. We're not asking whether the science is worth it. We're asking something more fundamental than either of those things. We're asking whether the basic laws of nature would ever permit anyone to go and come back. And when you run the numbers honestly, when you sit down with the actual math and the actual biology and the actual mechanics of what a round trip to Neptune demands, the answer that comes back is deeply uncomfortable. By the end of tonight, you're going to understand exactly why. We're going to walk through every piece of this. The distance, which is larger than most people can genuinely process. The travel time, which consumes a significant portion of a human lifetime in each direction. The radiation accumulating in the crew's bodies across decades in deep space. The life support systems that would need to run flawlessly for 25 years or more without resupply, without rescue, without any real-time help from Earth. The fuel requirements that cascade into numbers our best rockets can't come close to meeting. And at the end of all of it, we're going to confront what it would genuinely signify to arrive at Neptune. Look out at a dim, storm-racked world where the sun is nothing more than a bright star in a black sky. Understand that you're not coming home. This is one of the most sobering calculations in all of human exploration, and it deserves to be taken seriously. Before we get into it, if you find yourself as fascinated by the outer solar system as we are, take a second to like the video or subscribe to the channel. It's a small thing, but it genuinely helps us reach more people who want to think seriously about where we are and where we might one day go. It means a lot. Now, let's begin. Neptune sits at the outer edge of our solar system, about 2.8 billion miles from the Sun, which puts it roughly 30 times farther from the Sun than Earth is. That number, 2.8 billion miles, sounds large in the abstract, but it doesn't really land until you start breaking it down into pieces that your brain can actually work with. So let's do that. Start with light. Light moves at 186,000 miles per second. It's the fastest thing in the universe, and nothing we've ever built comes within a fraction of that speed. When sunlight leaves the surface of the sun, it reaches Earth in about 8 minutes. That's why we talk about sunlight as something almost instantaneous. You step outside, and you're receiving energy that left the sun while you were still finishing your morning coffee. Now ask what happens when that same light keeps going, past Earth, past Mars, past the asteroid belt, past Jupiter and Saturn and Uranus. By the time it reaches Neptune, more than 4 hours have passed. Not minutes, hours. The light warming your face right now left the sun before that light even entered Neptune's atmosphere. Here's what that means for how Neptune looks. The sunlight arriving there is roughly 900 times dimmer than what we experience on Earth. High noon on Neptune, the moment when the sun is at its highest point in the sky, would look like deep twilight here. Not a cloudy afternoon. Deep twilight, the kind of dim gray you see just before stars become visible. The sun itself, seen from Neptune's vicinity, would appear as a very bright star. Not a disk, not the warm, overwhelming presence it is from Earth's surface. Just a bright point of light in a dark sky, indistinguishable in shape from the other stars around it, except that it outshines everything else in view. Now let's talk about the distances humans have actually traveled. The farthest we have ever sent a person is the moon. The Apollo astronauts traveled roughly 240,000 miles to get there, a journey that took about 3 days each way. At the time, that felt like the edge of everything reachable. It was an extraordinary technical achievement, and it still is. But 240,000 miles compared to 2.8 billion miles is not a different point on the same scale. It's a different category entirely. If the distance from Earth to the moon were 1 inch, the distance from Earth to Neptune would be roughly 980 feet, nearly the length of 3 football fields. The moon isn't a stepping stone to Neptune. It's essentially still in Earth's backyard. Even when you compare Neptune's distance to other destinations in the solar system, the numbers are staggering. Mars, which is considered the obvious next destination for human spaceflight, sits between 35 and 250 million miles from Earth, depending on where both planets are in their orbits. Even at its farthest, Mars is a small fraction of Neptune's distance. Getting to Mars would take months. Getting to Neptune takes years, and that's with the best trajectories available to us. Here's the thing most people don't stop to consider. The figures we've been using describe Neptune's average distance from the Sun. But what matters for a mission is the distance between Earth and Neptune at the time of travel, which changes constantly as both planets move in their orbits. At their closest possible approach, when both planets line up on the same side of the Sun, the gap between them is still about 2.7 billion miles. That's the minimum. The best-case scenario. When they're on opposite sides of the Sun, the distance stretches to over 2.9 billion miles. There is no shortcut. There is no favorable season where Neptune becomes meaningfully closer. The distance is enormous, no matter when you go, and it compounds everything else. Communication signals, which travel at the speed of light, take over 4 hours to cover the distance one way. That means a message sent to a crew near Neptune takes 4 hours to arrive, and the reply takes 4 hours to come back. You are not just isolated by space, you're isolated by time. Every question, every emergency, every conversation with the people you left behind is separated from its response by nearly half a day. The psychological weight of that alone, the experience of sending a message and waiting 8 to 9 hours for any response, is difficult to fully imagine if you've never been more than a few light seconds from Earth. There's a specific number worth sitting with for a moment: 4.5 billion kilometers. That's roughly what separates Neptune from the Sun in metric terms, and it's close enough to Earth's separation from Neptune that the distinction almost doesn't matter at this scale. 4.5 billion kilometers. The circumference of Earth is about 40,000 kilometers. You would have to circle the Earth more than 100,000 times to cover the distance to Neptune. That's not hyperbole designed to sound dramatic. That's the actual math. and it's worth letting it settle in before we move on to what it means for a crew trying to complete the journey and then come home. Because the distance isn't just an obstacle on the way out, it waits for you on the return trip. Every mile that separates Neptune from Earth has to be covered twice. All the fuel, all the time, all the physical and psychological cost. It doubles. And as we'll get to shortly, the math of doing that at all may not actually work. That's not just a number on a page. It's a sentence for anyone who goes. The only spacecraft that has ever visited Neptune is Voyager 2. What it found when it got there is still, more than 3 decades later, essentially the best close-range data we have on the 8th planet. Voyager 2 launched in August 1977. That's not a typo. The probe that gave us our only close look at Neptune left Earth nearly half a century ago, before the personal computer existed, before the internet, before most of the scientists who analyze its data today were born. It traveled for 12 years before it reached Neptune, arriving on August 25, 1989. The reason it got there in 12 years rather than 30 is a piece of cosmic luck that won't repeat itself for well over a century. Here's the thing most people don't realize about that mission. The trajectory Voyager 2 flew, swinging past Jupiter, then Saturn, then Uranus, each planet bending its path and adding velocity, required a specific alignment of the outer planets that occurs roughly once every 176 years. The scientists at NASA in the 1970s recognized that window was open and built an entire mission around it. They had to. Without those gravity assists, the same trip would have taken approximately 30 years using the technology of the era. The alignment did the work that no rocket could. And when it closed for generations. So Voyager 2 arrived at Neptune in the summer of 1989, and then it left. That's the part that's easy to overlook. This wasn't an orbital mission. There was no slowing down, no settling into orbit, no extended survey of the system. Voyager 2 came screaming past at flyby velocity, tens of thousands of miles per hour, and humanity had a few hours of close-range observation before the probe continued on its way into interstellar space. A few hours. That's the entire database of close-range Neptune science. A few hours in 1989. What those hours revealed was genuinely extraordinary. Neptune's atmosphere turned out to be one of the most violent environments in the solar system. Wind speeds reached up to 1,500 miles per hour, 9 times the force of Earth's most powerful hurricanes. Driven by dynamics that scientists still don't fully understand, especially given how little sunlight Neptune receives. The planet generates significant internal heat, which appears to be part of what's driving those winds. But the exact mechanism remains an open question. Even with the best data we have, Neptune's weather is largely a mystery. Voyager 2 also photographed a massive storm system in Neptune's southern hemisphere. Scientists called it the Great Dark Spot. It was large enough to contain the entire Earth inside it. Think about that for a second. One storm on one planet, big enough to swallow our world whole. By the time the Hubble Space Telescope turned toward Neptune in the 1990s, the Great Dark Spot had vanished and new storms had appeared in different locations. The atmosphere is that dynamic, that restless, even at 2.8 billion miles from the Sun. Then there was Triton. Neptune's largest moon turned out to be one of the strangest objects Voyager 2 encountered in its entire journey through the solar system. The surface temperature registered at minus 391 degrees Fahrenheit. That's minus 235 Celsius. It's one of the coldest natural bodies ever measured anywhere in the solar system. cold enough that nitrogen freezes solid on the ground. And yet Voyager 2 photographed active geysers shooting nitrogen ice and dark organic material more than 5 miles into the sky. A moon so cold that nitrogen is a solid and it's geologically active, erupting in the outer solar system at temperatures that approach absolute zero. Triton also orbits Neptune backward in the opposite direction of the planet's rotation. That retrograde orbit tells scientists it wasn't formed alongside Neptune the way most moons form. It was captured. Probably a Kuiper Belt object, something like a larger cousin of Pluto. That wandered too close to Neptune billions of years ago and got pulled in. The capture event would have been violent, generating enormous tidal heating that may have liquefied Triton's interior and reset its surface. What Voyager 2 saw was a moon that looked young in places, geologically active and deeply strange. Since 1989, no spacecraft has returned to the Neptune system. Not a flyby, not an orbiter, not even a dedicated observation mission. As of today, there is no confirmed future mission to Neptune on any space agency's schedule. Proposals have been made. The Neptune Odyssey concept has been discussed seriously among planetary scientists, but nothing has been approved, funded, or built. The 8th planet is sitting out there, 2.8 billion miles away, with winds that would shred any aircraft ever designed and a moon that erupts nitrogen at temperatures near absolute zero. Our entire scientific understanding of that system is based on a few hours of rushed observation from a spacecraft that has long since left the solar system entirely. Everything humanity knows about Neptune fits inside a few hours of flyby data from a single spacecraft that launched before most of the people reading about it were born. So let's talk about what it would actually take to get there, starting with how long. Voyager 2 is our only real benchmark. It launched in 1977 and reached Neptune in 1989. That's 12 years, and it only managed that because the planets happened to be arranged in a configuration that occurs once every 176 years. Jupiter, Saturn, and Uranus were lined up in a way that allowed Voyager to slingshot from one to the next, borrowing speed from each planet's gravity and arriving at Neptune far sooner than any direct trajectory would have allowed. Without those gravity assists, the mission scientist estimated the trip would have taken closer to 30 years. Voyager 2 didn't slow down. It didn't stop. It screamed past Neptune at flyby velocity, gathered what data it could in a matter of hours, and kept going. That's how it made 12 years work. A crewed mission is an entirely different problem. Here's the thing most people don't immediately think about. When you send humans somewhere, you can't just fly past. You have to slow down when you get there. Decelerating from interplanetary cruise speed requires fuel, a lot of it, and that fuel has to travel with the spacecraft from the moment it leaves Earth. More fuel means more mass. More mass means you need more thrust to accelerate. More thrust means more fuel to power that thrust. The numbers start compounding very quickly, and every compounding step adds time to the mission. The lightest, most efficient crewed mission to Neptune that anyone has proposed, using a Jupiter gravity assist and pushing the spacecraft technology well beyond what we currently have, still puts the one-way travel time somewhere between 12 and 16 years. That assumes the launch window lines up. That assumes the propulsion works exactly as planned. That assumes nothing goes wrong for over a decade of continuous spaceflight. So let's say 14 years, splitting the difference. You leave Earth. You spend 14 years in transit. You arrive at Neptune. Now what? You can't just turn around. You've spent 14 years in a spacecraft to get there. The mission would need at minimum several months, more realistically a year or more, to conduct the science that justified the entire undertaking. Deploy probes into Neptune's atmosphere, study Triton at close range, run the measurements and observations that robotic spacecraft simply can't perform with the nuance a human crew can bring, and then you have to prepare to leave, which means checking every system, calculating your departure window, and making sure you have enough fuel and resources for a return journey that's equally long. We're looking at a minimum of about 12 to 16 years back. Add that up. 14 years out, 1 year at Neptune, 14 years back. That's 29 years. Call it 30. Think about that for a second. 30 years. That's not an abstraction. Let's make it concrete. Say you're 35 years old when you strap in and leave Earth. You are in good health. You are at the top of your professional abilities. Your parents are probably in their 60s. Maybe you have young children, 5 years old, 8 years old. Maybe you don't, because mission planners would almost certainly counsel against it. You launch. The Earth shrinks behind you. You pass the moon in a matter of hours. You're gone. You arrive at Neptune at 49. Your parents, if they're still alive, are in their late 70s or 80s. The children you left behind are adults with their own lives, their own jobs, their own relationships. If you had a 5-year-old when you launched, that child is now 19 and has grown up without you. You've missed everything, every birthday, every milestone, every ordinary Tuesday that makes up a life. They know you through video messages that took hours to transmit each direction. They know you the way you know a relative you met a handful of times in childhood. You've been a voice from a screen, and you haven't come home yet. You've just arrived. You have to do the work, and then you have to make the trip back. You'd leave Neptune at 50, 51, depending on how long the mission at the planet takes. If everything holds together and you make it back, you step off that spacecraft at 65, assuming your body has held up, assuming the radiation hasn't taken too much, assuming the 2.5 decades of recycled air and artificial light and the psychological weight of that kind of isolation haven't broken something that can't be repaired. Your parents are almost certainly gone. Your children are approaching middle age. You're an old person in a world that has moved on without you for 3 decades. The technology has changed. The culture has changed. The people you knew have changed or died. You'd be a stranger in the only place you ever called home. That's the best case. That's if everything goes perfectly. And here's what makes it even more stark. The 30-year number assumes the return trip is physically possible at all. It assumes the spacecraft still has enough fuel. It assumes the life support systems can sustain the crew for another 14 years after the outbound leg. It assumes no one has died, no critical system has failed beyond repair. No catastrophic event has fundamentally changed what the mission can do. All of that is a separate set of problems from the travel time itself. We've only talked about how long. We haven't talked about the fuel required to make a return happen. We haven't talked about what the spacecraft needs to carry from day one to make both legs of that journey possible. We haven't talked about the orbital mechanics that dictate not just how long the trip takes, but when, specifically, you're allowed to leave. And that's before you've thought for even a moment about what happens when you try to come home. The journey to Neptune isn't just long, it's constrained in ways that most people don't realize. When most people imagine a mission to Neptune, they picture engineers finishing the spacecraft, loading the crew, and launching when everything is ready. That's not how it works. You can't just go when you're prepared. You can only go when the planets allow it. And the planets are not especially accommodating. Here's the thing most people don't realize about deep outer solar system missions. Getting to Neptune efficiently requires help from Jupiter. Not metaphorical help, literal physical momentum borrowed from the largest planet in the solar system. Without that assist, the math on a Neptune mission gets dramatically worse in ways we'll get into shortly. And Jupiter is only in the right position to provide that help during specific windows that open roughly once every 12 years. The last one ran from about 2014 to 2019. The next one opens around 2031. After that, you're waiting again. Think about what that means practically. You spend years designing the spacecraft. You recruit the crew and put them through a decade of training. You source the fuel, assemble the hardware, test every system. And all of that has to be finished and ready before a window that nature has already scheduled without consulting you, and will close on its own schedule whether you're ready or not. Miss it by a year, by 6 months, by a single major technical setback, and you don't delay the launch by a few months. You delay it by more than a decade. A funding gap in year 8 of development doesn't just set the program back. It potentially kills an entire generation's chance to go. So how does a gravity assist actually work? The spacecraft approaches Jupiter on a carefully calculated trajectory. As it gets close, Jupiter's enormous gravitational pull accelerates the craft, swinging it around the planet and flinging it outward toward the outer solar system. The spacecraft gains speed, real, significant speed, essentially by stealing a tiny fraction of Jupiter's orbital momentum. Jupiter is so massive that it doesn't noticeably slow down. The spacecraft, though, arrives at Neptune years sooner than it otherwise would. Voyager 2 used exactly this technique, along with assists from Saturn and Uranus, and that's the only reason it reached Neptune in 12 years, instead of something closer to 30. For a crewed mission, the gravity assist isn't a luxury, it's close to a requirement. Without it, you need to carry enough propellant to accelerate the spacecraft to Neptune crossing velocity entirely on your own engines. That means more fuel. More fuel means a heavier spacecraft. A heavier spacecraft needs more thrust. More thrust requires still more fuel. The numbers spiral fast, and all of that extra mass has to be launched from Earth's surface, which is already one of the hardest parts of any deep space mission. The gravity assist shaves years off the journey and removes a staggering amount of mass from the fuel budget. Miss the Jupiter window, and you're not just taking a longer route. You're building an entirely different and substantially more expensive spacecraft. The 2031 window is the one that serious mission planners are watching right now. Proposed robotic missions like Neptune Odyssey have been designed around it. A crewed mission would need to be in an advanced state of readiness well before that date, because you're not finishing the spacecraft and then launching. You're launching on the schedule the solar system has already set. And here's where this gets even harder for human missions specifically. Robotic spacecraft can sit in storage for a few years if a window slips. Crew members cannot. The people training today for a hypothetical 2031 departure are already aging. Push the launch to 2043, and you need a different crew, which means starting a significant part of the training program over, which costs time and money, which could threaten the next window. The whole process can collapse in on itself. The 12-year cycle also means the decisions made now about funding, about technology development, about political commitment to deep space exploration have consequences that don't just affect the next mission. They affect whether there is a next mission, because there are only so many windows in a generation, and letting one pass isn't a minor setback. It's a generation's opportunity spent. This is one of the things that makes Neptune so different from destinations like the Moon or Mars. Those missions can, in principle, launch on relatively flexible timelines. Neptune doesn't work that way. The architecture of the solar system imposes a schedule, and the schedule doesn't negotiate. Orbital mechanics don't care about your schedule, your funding cycle, or how long the crew has been in training. Here's where things start to get genuinely uncomfortable. We've talked about the distance, we've talked about the orbital mechanics, the launch windows, the narrow corridors of opportunity that only open once every 12 years. But all of that assumes you can actually build something that gets there. And that's where the rocket equation enters the conversation, and it doesn't leave. Here's what the rocket equation tells you. To accelerate any mass through space, you need fuel. But fuel has mass too. So you need more fuel to move the fuel, and that additional fuel has mass, which requires even more fuel to accelerate it. You see where this goes. It's not a linear relationship, it's exponential. Every kilogram you add to a spacecraft doesn't just require 1 kilogram of extra fuel. It cascades upward through the entire fuel budget in a way that punishes ambition at every step. For a mission to Neptune, that cascade becomes overwhelming. Think through everything a crewed spacecraft would need to carry. Fuel to accelerate out of Earth's orbit and onto a trajectory toward the outer solar system. Fuel to decelerate when you arrive at Neptune, because unlike Voyager 2, you can't just fly past. You need to actually stop, enter orbit, and stay. Fuel for maneuvering within the Neptune system. Fuel for departure when you're ready to leave. And then fuel for the return journey. All of it. The full 12 to 16 years back, including deceleration as you approach Earth again. That's 5 distinct fuel budgets, each one dependent on the mass created by all the others. And the fuel isn't even the heaviest part. Consider what 25 to 30 years in space actually requires. You need life support hardware, oxygen generators, carbon dioxide scrubbers, water recycling systems. You need habitat modules large enough for a crew to live in without going completely insane. You need medical facilities. You need food production systems. You need radiation shielding, which is dense and heavy. You need communications arrays, navigation computers, scientific instruments, backup systems for all of your primary systems, and backup systems for your backups. All of that mass goes into the rocket equation, and all of it demands more fuel, which demands more fuel to carry the fuel. Here's a number that helps put this in scale. The International Space Station weighs roughly 420,000 kilograms. It is the largest structure humans have ever built in space. It took more than a decade to construct, required over 40 separate launches from multiple countries, and it orbits just 250 miles above Earth's surface. It does not carry its own propulsion system for deep space travel. It does not carry fuel for a 30-year round trip. It cannot generate enough power to sustain a crew beyond Earth orbit. And yet it is roughly the scale of what you'd need just for the living quarters and life support portion of a Neptune mission, before you've added a single kilogram of propulsion hardware or return fuel. A crewed Neptune spacecraft would need to be substantially heavier than the ISS. No single rocket that exists today could put it into orbit. No single rocket currently on the drawing board could do it either. What you're looking at is a spacecraft that would need to be assembled in orbit, component by component, over a period of years from dozens of separate launches, each one expensive, each one carrying risk of failure, each one adding to the construction timeline before the mission even begins. And here's the part that gets quietly staggering when you sit with it. That assembled spacecraft, that orbital construction project that took a decade to build, it still needs to carry all 5 of those fuel budgets. The ISS analogy gives you a sense of the habitat scale. The propellant load would dwarf it. With conventional chemical rockets, you'd be looking at a propellant mass that makes the rest of the spacecraft look like a footnote. The ratio of fuel to everything else in a Neptune mission approaches numbers that are genuinely difficult to state without sounding like an exaggeration. chemical rockets, the kind we've used for every crewed mission in history, convert chemical energy into thrust. They're reliable, we understand them, they work. But they're also fundamentally limited in how much energy they can extract from a given mass of propellant. That limitation is a physical ceiling set by the chemistry itself. And for a mission to Neptune, that ceiling is simply too low. You can't brute force your way to 2.8 billion miles with hydrogen and oxygen combustion. The fuel requirement becomes so enormous that the concept collapses under its own weight before it ever leaves the ground. There are people who have run the numbers on what a crewed Neptune mission would require in terms of launch mass with conventional propulsion. The figures are high enough that they make the problem seem almost academic, not a question of how much money you spend, but a question of whether the thing is physically possible at the scale human civilization can currently achieve. So you're left with a clear conclusion. You can't reach Neptune with a human crew using the rockets we have today. You probably can't reach Neptune with a human crew using any rocket design currently in active development. The mass fractions don't work. The fuel budgets don't work. The launch infrastructure that would be required to assemble such a spacecraft doesn't exist and would take decades to build. And all of that is before you ask a single question about what powers the spacecraft once it's out there, or how you keep the crew alive for 3 decades, or what propulsion gets you there in a time frame where the crew is still alive upon arrival. The math doesn't care how determined you are. It just tells you what you need. And right now, what you need doesn't exist. The most grounded option is nuclear thermal propulsion. Here's the idea. Instead of burning chemical fuel to generate thrust, you run a nuclear reactor and use the heat to superheat hydrogen propellant, which then shoots out the back of the engine at very high velocity. It's real technology. The United States actually tested nuclear thermal engines in the 1960s under a program called NERVA. They worked. Nuclear thermal engines are roughly twice as efficient as the best chemical rockets we have today, which means you need less propellant to achieve the same velocity change. That's a meaningful improvement. But twice as efficient as a chemical rocket still isn't fast enough for a crewed Neptune mission in any reasonable time frame. You'd shave years off the journey, not decades. The trip to Neptune would still take the better part of a human lifetime, and you'd still be dealing with every other problem on the list. Nuclear thermal propulsion is probably the most realistic near-term upgrade we could make to deep space travel. It's just not the leap we need. Then there's nuclear pulse propulsion. This is Project Orion, first seriously studied in the late 1950s and into the 1960s. The concept is exactly what it sounds like. You detonate nuclear bombs out the back of your spacecraft one after another and absorb the blast with a massive plate mounted on shock absorbers. The repeated explosions push the ship forward. Computer modeling suggested this could work and work well. Some estimates put potential velocities at several % of the speed of light, which would get you to Neptune in a fraction of the time any other method could manage. The physics isn't wrong. The problem is everything else. You'd need thousands of nuclear warheads on board. The radiation exposure to the crew would be severe and ongoing. And then there's the 1963 Partial Nuclear Test Ban Treaty, which prohibits nuclear detonations in space. Project Orion was shelved not because the equations failed, but because the political and practical reality of building, launching, and detonating thousands of nuclear weapons in orbit made it essentially impossible. It remains on paper, a compelling idea that the world decided it wasn't willing to actually build. Fusion drives are what most people point to when they want a genuinely fast, genuinely clean solution. The sun runs on fusion. It fuses hydrogen into helium and releases enormous amounts of energy in the process. If you could harness that reaction in a compact engine, you'd have a propulsion system with incredible efficiency and a fuel supply, hydrogen that is essentially unlimited. The numbers work beautifully on paper. The problem is that we haven't achieved controlled sustained fusion here on Earth in a laboratory where conditions are optimal and engineers can work on it directly every single day. We have been trying for more than 70 years. Progress is real, and recent results from facilities like the National Ignition Laboratory are encouraging. But a fusion power plant that produces more energy than it consumes is still not operational. A compact fusion reactor small and light enough to fit inside a spacecraft engine is much further away. Even the most optimistic timelines put practical fusion rockets decades out. Decades we don't have if we're planning a mission around the next launch window. Dalwenti. Ion drives are different from the others in one important way. They're not theoretical. We've used them. The Dawn spacecraft used ion propulsion to orbit both Vesta and Ceres. Deep Space One used it. Ion drives work by ionizing a gas, typically xenon, and using electric fields to accelerate the ions out the back of the engine at very high speeds. They're extraordinarily fuel efficient. The exhaust velocity is much higher than any chemical rocket. The problem is thrust. The actual push an ion drive produces is tiny. We're talking about a force roughly equivalent to the weight of a single sheet of paper lying flat in your palm. Ion drives work by running continuously for months or years, very gradually building up speed. That's fine for a robotic probe where time is flexible. For a crewed mission, you'd need to scale the thrust up enormously. And to power an ion drive at that scale, you'd need a massive nuclear reactor on board, which adds weight, which requires more thrust, which requires more power, which requires a bigger reactor. The cascade runs in exactly the wrong direction. Solar sails and laser sails have a certain elegance to them. Photons carry momentum. When light hits a reflective surface, it transfers that momentum, producing a push. Build a sail large enough and thin enough, and you can be pushed by starlight. The Japanese Ikaro spacecraft actually demonstrated this in 2010. A laser array on Earth or in orbit could theoretically push a small sail-equipped craft to significant velocities. The Breakthrough Starshot Initiative has proposed doing exactly this with a microchip-sized probe. But for a crewed ship, the sail would need to be enormous, potentially hundreds of square kilometers, while also being incredibly light. Building that in space is a construction challenge of almost unimaginable scale. And beyond the inner solar system, the sun's light pressure drops off rapidly. By the time you're out past Jupiter, it's barely useful without a laser booster. The laser array powerful enough to accelerate a crewed spacecraft would require gigawatt-scale energy output and precision pointing across billions of miles. Here's the uncomfortable summary. The most realistic near-term option for reaching Neptune is still a chemical rocket with a Jupiter gravity assist, taking 12 to 16 years. Everything faster is either decades away from being ready or faces fundamental barriers that haven't been cleared. Every option that gets you to Neptune faster comes with a problem that hasn't been solved, and some of them come with problems that might not be solvable at all. There's another problem that doesn't get as much attention as propulsion, and it's one that doesn't have a simple answer. At Neptune's distance from the Sun, the available sunlight is roughly 900 times weaker than what we receive here on Earth. On Earth, solar panels work because the Sun is close enough and bright enough to push meaningful amounts of electricity through a circuit. At Neptune, that same Sun looks like a very bright star. Not a disk, not a source of warmth, just a point of light in a black sky. By the time that light reaches Neptune, there's almost nothing left to capture. Solar panels that would power a small building in Earth orbit would barely keep a single instrument running out there. For a crewed spacecraft, something with life support systems, heating, lighting, medical equipment, communications arrays, navigation computers, and a crew of people who need all of those things running simultaneously, continuously for 25 years. Solar power isn't just insufficient, it's irrelevant. So you need nuclear power. That's not a controversial statement among scientists who study deep space missions. Every serious proposal for a Neptune mission, robotic or crewed, converges on the same answer. The question isn't whether you use nuclear power, it's which kind and whether you can actually build it. The first option is a radioisotope thermoelectric generator, or RTG. These are the devices that have powered deep space probes for decades. Voyager 2 ran on RTGs, so did Cassini, New Horizons, and the Curiosity rover. They work by converting the heat released from radioactive decay directly into electricity. They're reliable, long-lived, and require no moving parts. The preferred fuel is plutonium-238, a specific isotope that produces steady heat over decades without dangerous levels of radiation penetrating the surrounding structure. Here's the problem. Most of the world stopped producing plutonium-238 in any meaningful quantity decades ago. The United States shut down its primary production program in the late 1980s, and the supply has been dwindling ever since. Even for robotic missions, scientists and mission planners have been raising alarms for years. If we want enough Pu-238 to power a Neptune orbiter, we needed to start producing it well before the launch window opens. We didn't, and even if you solved the production problem completely, RTGs still wouldn't be enough for a crewed mission. The power demands of a spacecraft keeping humans alive are categorically different from the demands of a probe running a handful of scientific instruments. You need heat to keep the crew from freezing. You need atmospheric processing systems running around the clock. You need lighting because humans deteriorate without light cycles. You need medical equipment on standby. You need computers managing every system simultaneously. You need communications equipment powerful enough to transmit across billions of miles. A standard RTG produces somewhere between 100 and 300 watts of electricity. A crewed spacecraft would need hundreds of kilowatts, possibly more. That's not a scaling jolly. And you solve by adding more RTGs. The mass alone would become unmanageable. What you actually need is a nuclear fission reactor, not a decay-based power source, but a controlled chain reaction generating real power outputs sustained over decades. Nuclear fission reactors for space applications have been tested before. The Soviet Union flew dozens of them, and the United States has operated small experimental systems. But nothing close to what a Neptune mission would require has ever been built, launched, or demonstrated in space. Designing a reactor compact enough to launch, powerful enough to sustain a crew, and reliable enough to run for 25 to 30 years without a major maintenance capability is an engineering challenge that remains genuinely unsolved. Then there's the heat problem. A nuclear reactor produces enormous amounts of waste heat that can't just be absorbed by the spacecraft. You have to radiate it away. In space, radiation is the only option. That means large panels extending from the spacecraft, specifically designed to shed thermal energy into the void. Those panels are fragile. They're exposed to micrometeorite impacts. They're exposed to the temperature extremes of deep space. They add significant mass. And if they're damaged, the reactor begins overheating, which cascades into every system that depends on it. The crew can perform limited repairs. They cannot rebuild a failing reactor core or replace a radiator panel that's been punctured by a high-velocity particle. The systems have to work. Not mostly, not usually. continuously without serious failure from the day the ship leaves Earth orbit until the day, if that day ever comes, it returns. If the reactor fails completely, you don't declare an emergency and wait for help. There is no help. The heating systems stop. The crew has hours before the temperature inside the ship drops below survivable levels. Atmospheric processing stops. Within that same window, the air becomes unbreathable. There's no sequence of backup plans that walks you back from a total power failure this far from Earth. Your nuclear reactor isn't just a power source, it's the heartbeat of the ship, and everything living on board stops the moment it does. Let's say, for the sake of argument, that you've solved the propulsion problem and you have a power source that actually works. Now you face something that might actually be harder. You have to build the ship itself. Not a spacecraft in the way we normally think about spacecraft, a pressurized tube with some instruments and a re-entry capsule at one end. Something categorically different, a structure that can keep human beings alive, functional, mentally intact for 25 to 30 years with no resupply, no rescue, no outside help of any kind. Think about what that list of requirements actually looks like. You need living quarters with enough personal space that people aren't driven to madness by proximity. You need workspaces and laboratories. You need full medical facilities, not a first aid kit, an actual surgery suite, diagnostic equipment, pharmaceutical stores. You need exercise equipment that the crew can use every single day for decades. This was because without it, their bodies deteriorate in ways that become irreversible. You need food production systems, water recycling, atmosphere processing, radiation shielding, navigation systems, communications arrays, repair workshops stocked with parts for systems that haven't broken yet. And you probably need dedicated psychological support spaces, somewhere quiet, somewhere that feels different from the rest of the ship. This was because the human mind needs variety, even when the environment offers almost none. Here's the thing most people don't realize when they picture a spacecraft. The International Space Station is roughly the size of a football field and weighs about 420,000 kilograms. It took over a decade to assemble, required more than 40 separate launches. It still functions primarily as a short-stay research outpost. Crews rotate out after 6 months. Resupply ships arrive several times a year. If something goes seriously wrong, there are evacuation capsules docked and ready. The ISS is an extraordinary engineering achievement, and it would be completely, utterly inadequate for a Neptune mission. Not because it's bad engineering, but because it was never designed to be a world. This ship would have to be. One of the most critical design problems is gravity. Without it, 25 years of weightlessness would reduce the crew to physical wrecks. Bone density loss, muscle atrophy, cardiovascular weakening, fluid shifts pressing on the optic nerve. These effects show up after 6 months on the ISS. Over 25 years, they wouldn't just be inconveniences, they'd be permanent, debilitating, and possibly fatal. The solution is a rotating section, a ring or cylinder that spins to create centrifugal force mimicking gravity. In principle, this works. In practice, it introduces a cascade of engineering complications. The rotating section has to interface with non-rotating parts of the ship. That means bearings, seals, and mechanical connections that have to hold together for decades. The Coriolis effect, a disorienting sideways force you feel whenever you move in a rotating environment, has to be managed by calibrating the rotation rate carefully. This was because too fast and the crew experiences constant nausea. Too slow when the artificial gravity isn't strong enough to do the job. And the whole structure introduces stresses that don't exist on a non-rotating spacecraft. stresses that compound over time on every weld and joint in the system. Thermal management is another problem that sounds straightforward until you work through it. Space is not uniformly cold. The forward face of the spacecraft, the side pointed in the direction of travel, absorbs radiation and particle flux from the interstellar medium. The rear sections radiate heat into a void that sits close to absolute zero, across a structure that might be several hundred meters long. You're managing extreme temperature gradients that shift as the spacecraft maneuvers, as systems power up or down, as the distance from the sun increases over years. Thermal expansion and contraction happen constantly. Every material in the ship expands slightly when warm and contracts when cold. Over 25 years, that cycling works on seams, on welds, on fasteners, on insulation. Materials that are rated to handle this for 5 or 10 years have to handle it for 3 times that long, in conditions more extreme than any Earth-based test can fully replicate. That brings us to material science, and this is where the problem gets almost philosophical. Every component on this ship, every bolt, every gasket, every circuit board, every meter of cable insulation has a rated lifespan. Engineers design systems with safety margins, but those margins assume the possibility of inspection, maintenance, replacement. On a Neptune mission, there is no replacement parts delivery. There is no return to port to swap out a failing component. The ship's repair workshops would carry spares for everything critical, but there's a hard limit to how many spares you can carry. 25 years is a long time for systems to fail in ways nobody anticipated. The crew would need to be engineers, machinists, fabricators in addition to everything else, capable of manufacturing replacement components from raw materials if necessary. And here's what that failure cost looks like in practice. On the ISS, a failed component is a problem. A repair team assesses it. Earth sends up a replacement and the crew installs it. On a Neptune mission, a structural failure in the hull, a crack in the rotating section's bearing assembly, a slow leak in a pressure seal. Any of these could move from manageable to catastrophic faster than the crew can respond. There is no margin, no backup from Earth, no option to abort and return. A problem that would be an inconvenience in low Earth orbit becomes a life or death situation 2 billion miles from home. So when you start to add it all up, the rotating gravity section, the thermal management systems, the medical facilities, the redundant life support architecture, the repair infrastructure, the radiation shielding, you're not describing a spacecraft anymore. You're describing a small civilization that has to function indefinitely without any external input. Every single system on board would need to work reliably not for 6 months or a year, but for longer than most people's marriages last. Food and water stand as perhaps our most vital requirements. They're ones that get solved last in conversations about propulsion and spacecraft design, even though without them, none of the rest of it matters. Let's start with water, because water is everywhere on a crewed spacecraft and also constantly disappearing. The ISS currently recycles roughly 93% of its water supply, pulling moisture from cabin air, processing urine, reclaiming condensation from every surface. That sounds impressive. For a mission lasting 6 months or a year, it's enough. But here's the thing. Most people don't think through. 93% recovery means 7% loss. Every day. Small numbers over short timelines look fine. Small numbers over 25 years become catastrophic shortfalls. If a crew of 6 loses even a liter of unrecoverable water per day across the entire mission, you're talking about thousands of liters gone. Water that has to have been stored in advance or produced on board because there's no resupply. For a Neptune mission, you'd need water recovery pushing 99.9%. Not 93, not 97, 99.9. That requires purification and recycling technology, operating at a level we haven't yet demonstrated in a sustained closed-loop environment. Every membrane filter degrades. Every processing unit accumulates mineral buildup. Every component in the recycling chain has a service life. Most of those service lives weren't designed with 25-year continuous operation in mind. Food is harder. You simply cannot carry 25 years of food for any crew of meaningful size. The mass alone would be prohibitive. Thousands of kilograms of provisions taking up volume and launch payload that could otherwise be structural material or fuel. So the food has to be grown. That means the spacecraft needs hydroponic or aeroponic growing chambers, sealed environments where plants grow under artificial lighting, fed nutrient solutions with their roots suspended in air or water rather than soil. The artificial lighting runs on your nuclear reactor. The nutrient solutions have to be formulated, monitored, and replenished. The plants produce calories and oxygen simultaneously. That makes them two critical systems wrapped into one, which sounds efficient right up until one of them fails. Crop failures on a Neptune mission aren't inconvenient. They're a compounding emergency. If your primary wheat or soybean crop collapses due to a fungal contamination or a lighting malfunction, you've lost calories and oxygen production at the same time, which is why you'd need redundant growing chambers, seed banks maintained under careful storage conditions, backup lighting systems, separate compartments where a failure in one can't spread to the others. The crew would eat a diet managed with an almost clinical precision. Caloric intake tracked, nutrient ratios monitored, variety limited by what could realistically be grown in an enclosed system with finite resources and finite space. Lab-grown protein would likely supplement the plant-based calories, aquaculture tanks for fish, algae cultivation, which is calorie-dense and grows quickly, but is also deeply unpleasant to subsist on exclusively. The point is that the menu is not assembled around preference. It's assembled around what keeps people alive and functional. After 10 or 15 years of it, that distinction matters psychologically as much as physiologically. Then there's oxygen. Plants provide some of it through photosynthesis, but not enough on their own for a full crew. Electrolysis, splitting water molecules into hydrogen and oxygen using electrical current from the reactor, provides the rest. Carbon dioxide from every breath the crew exhales has to be scrubbed from the cabin air continuously. This was because CO2 accumulation is lethal well before oxygen depletion becomes the immediate problem. The scrubbing systems run on chemicals that deplete over time and require replenishment. Some of the CO2 can be recaptured and fed back to the plants, closing part of that loop, but not all of it. Not without the kind of precision management that doesn't tolerate mechanical failures. Here's where it gets genuinely uncomfortable. All of these systems are connected. That's not a design feature, it's a vulnerability. If the grow lights fail, you lose food production and part of your oxygen supply. If the water recycling system begins degrading, the nutrient solutions for the crops become harder to formulate correctly. Crop yields drop. That reduces calories available to the crew, which reduces the crew's ability to physically maintain the systems. If the crew is running at reduced caloric intake, their cognitive performance drops, and the systems that require intelligent, attentive maintenance are now being monitored by people who are hungry, tired, operating in an environment where the margin for error keeps shrinking. Think about the timeline. The International Space Station has operated for over 2 decades, but it has never operated without resupply missions delivering fresh components, replacement parts, additional food, maintenance equipment every few months. It has never operated without the ability to evacuate the crew in an emergency. Its life support systems have been incrementally improved and partially replaced over its operational life. A Neptune spacecraft doesn't have any of that. Everything on board has to work for 25 years using the equipment that was loaded before departure. If a membrane filter in the water recycler develops a crack in year 18, the crew has to have a replacement on board. Or they have to fabricate one, or they have to route around it with a backup system that has itself been sitting unused for nearly 2 decades. Parts degrade in storage. Materials in a high radiation environment become brittle. The electronic controllers for these systems accumulate radiation damage that eventually causes errors. The engineering challenge isn't designing a system that works at launch. It's designing a system that still works on year 22 of a mission, operated by a crew who is aging and radiation affected and potentially experiencing the psychological strain of 2 decades of confinement. We've never run a truly closed-loop life support system at this scale for this duration without outside support. The ISS comes close in some respects, but it's not a real test of what a Neptune mission demands. We don't have a track record that says this is achievable. We have engineering projections, theoretical efficiency numbers, and a handful of small-scale experiments. That's not the same thing. You'd be betting the lives of everyone on board on the hope that every link in that chain could hold together for 2 full decades without a single failure you couldn't fix. Then there's the radiation. This one is worth spending some time on because it's probably the most insidious danger of the entire mission. Everything we've talked about so far, the fuel, the food, the water recycling, those are problems you can see and measure and, in theory, engineer around. Radiation is different. You can't watch it accumulate. You can't feel it happening. The crew members would go about their days running systems checks, tending the grow chambers, sleeping and waking and working. The whole time, silently, the deep space radiation environment would be doing its work on their bodies at the cellular level. Here's what you need to understand about where that radiation comes from. There are 2 main sources, and they're very different problems. The first is solar particle events, sudden eruptions on the sun that send waves of high-energy protons streaming outward through the solar system. These are intense but brief. With enough warning time, a crew could shelter in a more heavily shielded section of the ship and wait them out. The second source is galactic cosmic rays, and this is where things get genuinely complicated. Galactic cosmic rays are particles accelerated to near the speed of light by distant supernovae, neutron stars. Black holes scattered throughout the Milky Way and beyond. They don't come in bursts. They come constantly from every direction at all times for the entire duration of the journey. There's no shelter window. There's no warning. They're just always there, and the physics of stopping them is brutal. Most galactic cosmic rays are protons, which shielding materials can handle reasonably well, but a significant fraction are heavier atomic nuclei, iron, silicon, calcium, that have been stripped of their electrons and accelerated to a significant fraction of light speed. These particles carry enormous energy. They punch through almost any material you could practically put on a spacecraft. And here's the part that makes engineers want to sit down for a minute. When one of those heavy particles hits a thick shielding layer, it doesn't just stop. It shatters, producing a cascade of secondary particles, protons, neutrons, gamma rays that can actually irradiate the interior more severely than the original particle would have. So adding more shielding helps with some types of radiation and makes others worse. There's no configuration of passive shielding that solves the problem. It's a fundamental constraint of the physics. NASA currently sets a career radiation limit for astronauts based on an acceptable increase in lifetime cancer risk. Even on the International Space Station, that sits inside Earth's magnetic field and gets some protection from it. Astronauts on 6-month missions accumulate radiation doses that put them meaningfully closer to that limit. In deep space, beyond Earth's magnetic field, the dose rate is significantly higher. On a mission to Neptune, 25 years out and back. Operating continuously in the deep space radiation environment, the cumulative dose would exceed NASA's career limit many times over. Not slightly, not by a factor that careful management might address, by a factor that makes the career limit look like a rounding error. What does that actually mean for the crew? It means elevated rates of cancer, not a small elevation, a significant one. It means cataracts developing earlier and more severely. It means damage to the central nervous system, subtle cognitive changes, degraded reaction times, memory effects that accumulate slowly, but do accumulate. Some research on heavy ion radiation in animal models suggests that the cognitive effects of galactic cosmic ray exposure could be substantial enough to affect crew performance over the course of a multi-decade mission. You'd potentially have a crew trying to make critical decisions in year 18 of the mission, with brains that have absorbed 18 years of galactic cosmic ray bombardment. That's not a comfortable thought when the decisions they're making have no safety net. Here's the part that makes this particularly difficult to solve. The natural instinct is to add more shielding, build a thicker hull, line the habitat with water tanks or polyethylene, materials that are reasonably effective against certain radiation types, and you do get some benefit from this. But every kilogram of shielding you add is a kilogram the propulsion system has to accelerate to Neptune and back. More mass means more fuel. More fuel means a heavier spacecraft at launch. A heavier spacecraft means you need even more fuel to move it. The rocket equation cascades and the mission gets longer. And a longer mission means more time in the radiation environment. That means the crew accumulates a higher total dose. That means you want more shielding, which adds more mass. You can see where this goes. The shielding problem and the propulsion problem are not independent. They're locked together in a feedback loop that makes both worse simultaneously. There is no known technology that breaks this cycle cleanly. Active magnetic shielding, generating an artificial magnetic field around the spacecraft to deflect incoming particles the way Earth's magnetic field deflects them, is theoretically interesting but requires enormous power and has never been demonstrated at a scale useful for human protection. It's a concept, not a solution. And the crew would know all of this before they boarded. They'd know that every year they spent in transit was adding to a cumulative dose their bodies could not shed. Some of them would develop cancer. That's not a worst-case scenario. That's a near certainty given what we know about the deep space radiation environment. And then there's what happens to the human body itself, independent of radiation, which is a separate and in some ways more mundane problem. Astronauts who come back from 6 months on the International Space Station need weeks of rehabilitation just to walk normally again. Their legs have forgotten how to carry them, their cardiovascular systems have softened, bone density has dropped measurably, sometimes by several percent in a single 6-month rotation. And their vision, this one surprises most people, is often permanently altered by fluid shifts that increase pressure inside the skull in microgravity. 6 months does all of that. Now think about what 12 to 16 years of it would do. Here's where things get uncomfortable. Engineers designing a crewed Neptune spacecraft would almost certainly include a rotating section, a part of the ship that spins to simulate gravity through centrifugal force. In principle, that solves the problem. In practice, it creates new ones. The rotation rate has to land in an extremely narrow range. Spin too fast and the Coriolis effect becomes debilitating. Every time a crew member moves their head or reaches across their body, they feel a sideways force that doesn't match what their eyes are telling them. The result is persistent nausea, disorientation, and degraded cognitive performance. Spin too slowly, and the simulated gravity is too weak to actually maintain bone density and muscle mass over a decade. There's a narrow window where it works reasonably well, and even inside that window, the crew would be moving between rotating and non-rotating sections of the ship constantly, going to maintenance areas, instrument bays, EVA preparation chambers. Every transition means re-exposure to microgravity. Over years, that exposure accumulates. So let's say the rotating section works as intended. You still have a more basic problem. People age. The crew who launches in their mid-30s would arrive at Neptune approaching 50. That's not old, but it's the age when cardiovascular disease starts showing up, when joints begin to deteriorate, when vision and hearing change in ways that are gradual but real, when the body starts requiring more maintenance than it used to. On Earth, you manage those changes with specialist care, cardiologists, orthopedic surgeons, ophthalmologists. On this spacecraft, there are no specialists coming. There's no referral network. The ship carries whatever medical equipment was aboard at launch, operated by whoever among the crew has the deepest medical training, and that assumes nothing actually goes wrong. Think about what happens when something does. Appendicitis is a fairly routine emergency surgery on Earth. You go in, you come out, you recover. On this spacecraft, an appendicitis case means one of your fellow crew members is opening you up with equipment that has been in space for a decade, performing a procedure they may have trained for but have almost certainly never done on a living person. The outcome depends on their skill, on the quality of anesthesia that may have partially degraded, on whether the surgical tools are still properly calibrated, and on whether the recovery environment, the same recycled air, the same cramped quarters, doesn't introduce a post-surgical infection. A difficult fracture, a complicated delivery, a tumor requiring surgical removal. All of these would play out the same way. The crew would be simultaneously the hospital, the pharmacy, the surgical team, and the patient. Medications are a particular problem that doesn't get enough attention. Drugs have shelf lives. Many of them degrade significantly over 5 to 10 years, losing potency or becoming chemically altered in ways that can be harmful. A 25-year mission launched with a full pharmaceutical inventory would arrive at Neptune with medicines that are well past their rated effectiveness for many conditions. You can't resupply. You can manufacture some compounds on board if you have the equipment and the expertise, but you can't manufacture everything. The crew would be managing chronic conditions with whatever is left in the cabinet, adjusting doses to compensate for degradation, making educated guesses about what's still safe to use. The combination of these factors, degraded medications, aging providers, atrophied skills, and cumulative physical stress, creates a medical system that is fundamentally fragile and deeply inadequate. Unlike Earth hospitals that can call in specialists or contact poison control centers, the spacecraft operates as a closed system. Every decision about health is final in a way almost no medical decision on Earth can be. There is no higher level of care to escalate to, no second opinions to seek, no way to call for help. Here's the thing most people don't consider. The people performing the medical procedures aren't unaffected bystanders. They're dealing with the same cumulative physical stress as everyone else on board. A crew member who was a physician at launch is, 15 years later, a physician who has spent 15 years in space. Their hands may not be as steady. Their eyesight may have shifted. Their own cardiovascular health may have changed. You're asking someone who is themselves a product of this environment to provide care for people in the same environment. The doctor and the patient are both running down the same clock. By the time you arrived at Neptune, you might not be physically the same person who launched. And there's real uncertainty about whether you could function well enough to do the work the mission requires. Right now, Voyager 2 is so far from Earth that a radio signal from the spacecraft takes about 18 hours to reach us, and the same amount of time for our reply to reach back. That's a robotic spacecraft with minimal power requirements, no crew, and no emergencies to manage. For a crewed mission heading to Neptune, that number tells you something important about what communication actually means at these distances, and what it stops meaning. Here's the thing most people don't think about. The delay doesn't hit you all at once. It builds gradually, the way pressure builds as you dive deeper underwater. Early in the mission, when you're still in the neighborhood of Earth, communication is close to real time. A few seconds of lag, maybe a minute. You can have something resembling a conversation. You can call home. Mission Control can talk you through a problem in close to real time, the same way they do with the International Space Station. By the time you cross Jupiter, the delay is measured in minutes. 30, 40 minutes for a round trip. Annoying, but manageable. You can still pass instructions back and forth within a single work shift. Then you pass Saturn and it's tens of minutes each way. The rhythm of communication changes. You stop having conversations and start exchanging messages, more like letters than phone calls. By the time you're approaching Neptune, a one-way transmission takes roughly 4.5 hours. That's one way. A question sent to Earth at 8 in the morning doesn't get an answer until after 5 in the evening, and that assumes the people on Earth are immediately available, have the answer ready, and don't need to call a meeting, consult an engineer, sleep on it, or run a simulation. For anything beyond a simple factual query, you're realistically looking at responses arriving the next day or later. Think about what that means for an emergency. Something goes wrong with the reactor cooling system. You send a message to the best nuclear engineers on Earth. 9 hours later, you get their first response. You send a follow-up with the new readings. 9 more hours. The problem is either solved or catastrophic long before you've had 3 exchanges. The crew doesn't just need to be competent, they need to be capable of diagnosing and resolving virtually any technical failure on their own, from propulsion anomalies to medical crises, without waiting on the most knowledgeable people alive. That's a different kind of expertise than anything we've trained astronauts for. Right now, ISS crews operate with mission control available in real time. Someone on the ground is always watching the data. If a reading looks wrong, they call up and say so. That safety net doesn't exist at Neptune. The crew is the safety net. All of it. There's no one watching the screens back home who can catch what they miss. And then there's the personal dimension, which is harder to quantify but probably harder to live with. You send a message to your family, your partner, your children, whoever you left behind. The reply arrives 9 hours later. You respond again. 9 more hours. A single back-and-forth exchange takes the better part of a day. An actual conversation, one where you're reacting to what the other person just said, is essentially impossible. What you have instead is a slow-motion correspondence, like letters that happen to move faster than ships. Except the delay keeps growing as you travel farther out. A few years into the mission, news from Earth arrives hours old by definition. By the time you're halfway to Neptune, the world you left has been quietly changing in ways you're only catching up to in fragments. Political shifts, technological breakthroughs, cultural moments, all of it arrives through a filter of growing delay, growing compression. The sense that you are reading about a place rather than remaining connected to it. People you love are aging in real time while your knowledge of their lives is perpetually out of date. Eventually, the psychological weight of that becomes its own kind of burden. You're not cut off from Earth. You can still hear from it, still send messages, still receive news. but the connection is stretched so thin that it starts to feel like something fundamentally different from contact, more like receiving light from a distant star. The information is real, but it left its source a long time ago, and the crew has to keep functioning through all of it, has to maintain focus, technical precision, cooperative relationships, and the kind of stable mental health that a 25-year mission demands, while managing the constant low-level awareness that Earth is effectively unreachable in any practical sense. Not gone, just impossibly, increasingly far. The explorers of previous centuries faced isolation too, months at sea without news from home. But they could dock somewhere eventually, find a port, meet other people, send a letter through a passing ship. There was always the possibility, however remote, of stumbling into another human presence. On a spacecraft heading for Neptune, that possibility doesn't exist. There are no ports out there, no passing ships, no relay stations, no outposts, no signals from anyone else. Just the void in every direction and the crew inside a pressurized shell, handling everything themselves. You'd be more isolated than any human being who has ever lived. And unlike the explorers of previous centuries, you wouldn't even have the option of eventually finding your way to someone who could help you. Studies of isolated environments, submarines, Antarctic stations, the International Space Station, show a pattern that repeats itself with uncomfortable regularity. There's an initial phase where everything feels exciting. The mission is new, the crew is motivated, and every day brings something genuinely novel. People are operating at their best, performing well, supporting each other, feeling the weight of what they're doing. That phase ends. And on a Neptune mission, what comes after it has to sustain for somewhere between 20 and 30 years. Here's what the research actually shows. After the novelty fades, typically within the first few months, a conflict phase sets in. Small irritations compound. The way someone chews their food, the specific words they use when they're stressed, their tendency to leave equipment in the wrong place, things that seem trivial in training become sources of genuine psychological friction after months of constant proximity. In Antarctic winter-over studies, researchers have documented what they call the third quarter phenomenon, a marked dip in mood and cohesion about 3/4 of the way through an isolated deployment. The crew knows the end is coming, but it still feels distant. Motivation drops, conflict spikes, and people withdraw. On a 12-year outbound leg, that third quarter drop hits somewhere around year 9. And then you still have 3 years to go before you even arrive. Now think about what the crew actually experiences day after day. Every face in that ship is a face they've already seen 10,000 times. Every corridor has been walked so often the crew knows every scuff mark on every wall. Every conversation has been had before. You've heard every story, every opinion, every complaint. You know how each person laughs, how each person sounds when they're frustrated, exactly which topics will cause tension with which person. There's no one new to meet. There's no new place to go. For a crew that launched expecting 25 years of this, the psychological architecture of daily life has to be built from scratch. This was because nothing in human evolutionary history prepared us for the specific kind of confinement a Neptune mission demands. Romantic relationships are going to happen. Over a decade of close quarters, emotional bonds form that go beyond professional partnership. Some of those relationships will be healthy and stabilizing. Some will not. When they end, and some will end, the people involved don't get to avoid each other. They don't get separate apartments or different social circles. They share a habitat a fraction of the size of a typical school building. They have to keep doing their jobs together, attending the same meals. relying on each other for technical support, potentially trusting each other in an emergency with their lives. Mission planners would need to think carefully about that reality before it unfolds in deep space 8 years from home. And then there's the question of children on a 25-year mission with even a small crew. The statistical probability of pregnancies, planned or unplanned, is not negligible. We'll return to that question in more detail later in this discussion. But for now, consider what it means from a purely psychological standpoint. A child born on this mission didn't choose it. They have no concept of Earth except as an abstraction, a distant light that older crew members describe with nostalgia for a place they'll probably never see again. As that child grows up, what is their psychological frame of reference? The ship is their world. The crew is their entire society. And the mission, which the adults signed up for, is simply the only reality they've ever known. The leadership structure is going to be tested in ways that no command training fully anticipates. On Earth, when there's a serious disagreement, there are escalation pathways. You appeal to a higher authority, you request mediation, you take the matter to someone outside the immediate situation. On a Neptune mission, the command structure is the final authority because there is no other authority. If someone in a senior position makes a decision the crew believes is wrong, there's no appeal. If a crew member becomes mentally unstable, the options for managing that are severely constrained. You can't confine someone for years without losing their contributions to the mission. And in a closed system where everyone's life depends on everyone else performing their role. Even a partial withdrawal of labor or capability creates cascading problems. What happens in the extreme scenarios is something mission planners genuinely have to prepare for. Someone develops a severe psychiatric break, becomes paranoid, stops trusting the rest of the crew, begins interfering with systems. Someone becomes violent. Someone decides they are simply no longer willing to participate, not a performance issue, not a health issue, but a fundamental withdrawal of consent to be there. On Earth, those situations have institutional solutions. In the outer solar system, the crew is the institution. The decisions they would have to make in those cases have no clear precedent in any legal or ethical framework humanity has developed. This was because those frameworks all assume the possibility of outside intervention. The isolation from Earth also compounds every one of these psychological pressures. When you're 8 or 10 years into the journey, a message home and its reply cross 4.5 hours each way. You send your mother a message on her birthday, and her response arrives 9 hours later. The emotional texture of that exchange, the long silences, the awareness that the conversation is happening in installments separated by half a day, changes the nature of human connection in ways that are difficult to fully imagine. Over years, the relationships people have with family back on Earth don't sustain the way they would with more regular contact. Marriages end via transmissions that take hours to arrive. Children grow up in photographs. The crew becomes, over time, each other's only real social world in any functional sense. And that means everything that goes wrong inside the ship stays inside the ship. Every conflict, every grief, every psychological fracture, every small cruelty or disappointment, it all recirculates in the same sealed environment with the same small group of people for years, with no dilution and no escape. Mission planners can screen for exceptional psychological resilience, and they will. They can provide therapy protocols, communication tools, structured routines designed to maintain mental health. All of that will help. None of it will be enough to fully compensate for the fundamental reality of what this is. It is decades of confinement at an incomprehensible remove from everything familiar, with no exit option of any kind. and there is nowhere to go. No transfer request, no rotate, ion home, no door you can walk out of. Let's talk about what actually waits at the end of all of this, what Neptune is, what it does, what arriving there would actually look and feel like. After 12 to 16 years of travel, after the radiation accumulation and the recycled air and the psychological weight of confinement, you'd finally close the distance. Neptune would fill your viewport for the first time, and here's what you need to understand about what you'd be looking at. Neptune is not a solid planet. There's no ground, there's no surface to approach, no terrain to study from above, no place to put a lander. What you're looking at is a ball of water, ammonia, methane ice wrapped in a deep atmosphere of hydrogen, helium, and methane gas. The boundary between the atmosphere and the interior below isn't a surface. It's just a gradual transition from gas to something denser and hotter. There's nowhere to land because there's literally nothing to land on. The atmosphere itself is violent in a way that has no parallel anywhere else in the solar system. Neptune's winds reach speeds of up to 1,500 miles per hour. That's 9 times faster than the most powerful hurricanes on Earth. To put that in perspective, a Category 5 hurricane on Earth produces winds of around 157 miles per hour. We consider that catastrophic. Neptune's atmospheric winds are nearly 10 times that. And here's the thing that makes this even harder to process. Neptune receives less than 0.1% of the sunlight that Earth does. Solar heating drives most of Earth's weather, but Neptune is barely getting any sunlight at all. So why are the winds so extreme? Neptune generates its own internal heat. The planet radiates about 2.6 times more energy than it receives from the sun. That means something deep in the interior is producing heat independently, though exactly what mechanism is responsible remains poorly understood. That internal energy drives atmospheric circulation in ways we can't fully model. The result is the fastest sustained winds in the solar system churning through an atmosphere made of gases we could never breathe. When Voyager 2 flew past in 1989, it photographed what scientists called the Great Dark Spot, a storm system large enough to contain the entire Earth. That specific storm had already disappeared by the time the Hubble Space Telescope looked at Neptune a few years later. New storms have appeared and vanished since. These are dynamic, massive, and completely unpredictable. A crew arriving at Neptune would be looking at a planet whose weather systems can erase continent-sized storm features and generate new ones over timescales of years or decades. The cold is another thing entirely. Temperatures in Neptune's upper atmosphere drop to around minus 218 degrees Celsius, which is minus 360 degrees Fahrenheit. At that temperature, most materials you'd want to use for spacecraft hardware become brittle and unreliable. Any probe you deployed into the atmosphere would be destroyed almost immediately, crushed by increasing pressure, frozen by extreme cold, shredded by wind speeds that would reduce a conventional aircraft to fragments in seconds. And then there's the light. At 2.8 billion miles from the Sun, you're 30 times farther out than Earth. The Sun, which from Earth appears as a warm disk roughly half a degree across in the sky, would shrink to something indistinguishable from a very bright star. It would give almost no warmth. High noon on Neptune looks like deep twilight. The crew looking out at the planet would be doing so in a kind of permanent near darkness, lit only by that bright pinpoint of the distant sun and whatever artificial lighting the ship provided. Here's what that means practically for a crew in orbit. You'd be confined to the spacecraft, completely and permanently. You could run observations. You could deploy atmospheric probes, watch them descend on telemetry. receive data for as long as they survived the conditions. You could photograph the storm systems from orbit and watch them evolve. You could measure the magnetic field, sample the upper atmosphere remotely, map the rings — Neptune has a faint ring system — and compile the most detailed scientific record of the planet ever assembled. All of that would be genuinely extraordinary science. But you'd never step outside. Not for a moment. There's no surface to EVA to, no object to anchor a tether to, no physical thing to touch. The instruments would do the touching for you. After 12 to 16 years in transit, the destination itself would be something you could only observe through glass and sensors. Like every image humanity had already taken of it from Earth, just closer. That's not nothing. The data would be transformative. But for the humans who got there, the psychological weight of arriving at a destination that offers no physical contact, no ground beneath your feet, no possibility of even briefly standing somewhere new after more than a decade of travel. That's a particular kind of difficult to fully reckon with before you've lived it. Neptune isn't hostile the way Mars is hostile, where you could, in principle, put on a suit and stand on the surface. It's hostile in a way that simply rules out any possibility of humans ever standing on it at all. Neptune has 16 known moons, but one of them is unlike anything else in the solar system, and it's probably the most compelling scientific target the entire Neptune system has to offer. Its name is Triton, and the first thing you need to understand about it is that it orbits Neptune backward. Every other large moon in the solar system moves in the same direction as its planet's rotation. Triton goes the other way. That retrograde orbit is a fingerprint. It tells us almost certainly that Triton didn't form alongside Neptune the way our own moon formed near Earth. It came from somewhere else. The leading theory is that Triton was once a Kuiper Belt object, a distant icy body drifting in the outer solar system, until Neptune's gravity reached out and captured it billions of years ago. Think of Pluto. Triton is almost certainly a close relative, the same kind of object, just one that didn't escape. Here's where things get uncomfortable. That capture event wasn't gentle. When Neptune grabbed Triton, the gravitational interaction generated enormous tidal stresses, forces that would have heated Triton's interior to the point of partial melting, reshaping the moon from the inside out. Whatever structure Triton had before its capture was essentially erased. What we see today is a body that was violently remade by the collision of two gravitational worlds. And what Voyager 2 found when it got there in 1989 was genuinely strange. Triton is the coldest known natural body in the solar system. Surface temperatures hit minus 391 degrees Fahrenheit, minus 235 Celsius. At that temperature, nitrogen doesn't exist as a gas the way it does in Earth's atmosphere. It freezes solid. The surface is coated in nitrogen ice, methane ice, carbon dioxide ice. It is, by any ordinary measure, a completely dead and frozen world. Except it isn't. Voyager 2 photographed active geysers on Triton's surface. Not water geysers. Nitrogen geysers, columns of material shooting more than 5 miles into the thin atmosphere, carried downwind by whatever passes for weather at the edge of the solar system. A moon cold enough to freeze nitrogen solid is somehow generating enough internal energy to blow material skyward. The mechanism isn't fully understood. The leading explanation involves solar heating, thin as it is at Neptune's distance. Even that faint sunlight may be enough to warm nitrogen ice just slightly below the surface, causing it to sublimate and build pressure until it vents. But there may also be residual tidal heating from the original capture event still working through Triton's interior hundreds of millions of years later. The surface texture that Voyager 2 photographed is what scientists call a cantaloupe terrain, a strange, pitted, wrinkled pattern unlike anything seen elsewhere in the solar system. Alongside those older formations are smooth plains of younger ice, suggesting that Triton has been resurfaced at various points in its history. Something is renewing it, and where there's geological activity, where there's internal heat, the question that always follows is the same one. Could there be liquid water somewhere beneath that frozen surface? Tidal heating from Neptune's gravity is real and ongoing. It's not impossible, and that is a sentence that tends to get scientists very interested very quickly. So you can see why, for any human mission reaching the Neptune system after 12 to 16 years of travel, Triton would be the target. Not Neptune itself, which has no surface to approach and an atmosphere that would destroy any vehicle. Triton at least has a surface. You could orbit it, study it, deploy landers, and potentially set down on it with equipment built to handle extreme cold. It would be, by an enormous margin, the most scientifically valuable thing you could do with the time you had. But let's be specific about what -391 degrees Fahrenheit actually means for hardware and for humans. At those temperatures, conventional metals become brittle and fracture under stresses they would normally absorb. Lubricants used in joints, motors, and mechanical systems freeze solid and stop working entirely. Rubber seals fail. Electronics behave unpredictably. Any equipment designed to land on Triton would need to be engineered from scratch for a thermal environment that has no parallel in any prior human space mission. The engineering margin for error is essentially zero. A landing system that functions at -200 degrees might fail completely at -235. That gap is not trivial. It is the difference between a successful surface operation and a lander that touches down and immediately stops working. And for a human being, any breach of thermal insulation at that temperature is not a survivable event. Not an emergency, not a crisis that buys you time to solve a problem. You have seconds. That's it. Triton is spectacular, genuinely one of the stranger and more intriguing objects in the entire solar system, and also completely, utterly lethal. Now let's confront the question that sits at the center of this entire conversation. You've made the journey. 12 to 16 years in transit, years orbiting Neptune and Triton, accumulating data, managing crises, watching your body age in ways no physician back on Earth can fully anticipate. Now you have to come home. And here's where the arithmetic becomes genuinely brutal. A round-trip mission doesn't require twice the fuel. It requires many times the fuel. Think about why. Every kilogram of return propellant is payload during the outbound leg. That payload has to be accelerated from Earth to Neptune, which requires fuel to move it. That fuel is also payload, which requires more fuel to move it. The cascade effect is exponential, not linear. Engineers call it the tyranny of the rocket equation, and at Neptune's distance, it doesn't just bite, it devours. Here's what the fuel math actually demands. You need propellant to accelerate away from Earth. You need propellant to decelerate when you reach Neptune, because flying past doesn't count. You have to slow down and achieve orbit. You need propellant to conduct any meaningful maneuvers in the Neptune system. Then you need propellant to escape Neptune's gravity and begin the return. And then you need propellant to decelerate again when you finally reach Earth, or you'll streak past at thousands of miles per hour and never stop. Every one of those burns has to be fueled by mass that was loaded onto the spacecraft at departure. The spacecraft capable of carrying all of that would be staggering in size. Nothing we've built or are close to building could lift it. But let's set the fuel problem aside for a moment and just talk about time. The return journey takes another 12 to 16 years. A crew that launched at 35 arrives at Neptune around age 47 to 51. then years of operations at Neptune, then 12 to 16 more years back. You're looking at a crew in their late 60s by the time they theoretically see Earth again, if they're alive at all. And that's the problem. Statistically, they wouldn't all be. After 25 years of accumulated radiation exposure, after decades of living in a closed system with limited medical resources, after the physical deterioration that no exercise regimen fully prevents, a meaningful percentage of any crew would not survive the return leg. The radiation dose alone, accumulated over a quarter century in deep space, would substantially elevate cancer rates. Some crew members would develop tumors years into the mission. Others would experience cardiovascular degradation severe enough to become life-threatening without the kind of specialist care that simply doesn't exist on the ship. You'd be asking people in their late 50s and early 60s, already compromised by the journey out, to endure another decade and a half in that environment. The numbers don't favor everyone making it back. Then there's a dimension to this that doesn't get discussed enough: the weight calculation. You launch in, say, 2050. You're 10 years into the journey somewhere past Jupiter, committed, unable to turn around. Back on Earth, engineers have a breakthrough, a new propulsion concept, nuclear pulse, compact fusion, something nobody predicted. Cuts transit time to Neptune from 14 years to 6. A follow-up mission launches in 2065. They arrive at Neptune before you do. They set up instruments, begin science operations, establish a communications relay. By the time you reach the Neptune system, you're not the first, you're the second. And everything you sacrificed, your youth, your health, your relationships, the life you left behind, it didn't get humanity to Neptune first. Technology moved faster than your ship. There's no good answer to that scenario. You couldn't know when you launched what the next decade of engineering would produce. But it's a real risk, and it's the kind of thing mission planners would have to reckon with honestly. The history of exploration is full of people who prepared for years only to be overtaken by circumstances they couldn't control. The harder truth is simpler than all of this, though. Even setting aside the fuel math, even setting aside the statistics of survival, even ignoring the weight calculation entirely, who comes back? People in their late 60s who have spent 25 or more years in a radiation-saturated microgravity environment, who left Earth as relatively young adults, who have watched their bodies change in ways that are only partially reversible. The Earth they returned to would not be the one they left. Everyone they knew when they launched would be a generation older. The cities would look different. The technology would be unrecognizable. The political landscape would have shifted in ways impossible to anticipate. Coming home after 25 or 30 years would not feel like coming home. It would feel like arriving in a foreign country where you happen to speak the language. The mission profile that gets humans to Neptune and back is not a mission that offers the crew their lives in any recognizable form. The journey out costs them their youth. The time at Neptune costs them their middle age. The return, if it happens at all, brings them back as old people to a world that has moved on without them. The journey to Neptune, by any honest analysis, is a one-way trip, not necessarily by philosophy or intention, but by the unforgiving arithmetic of rocket fuel and human biology. There's a question that mission planners would have to wrestle with before anyone sets foot on that spacecraft, and it goes beyond propulsion or life support. On a mission that lasts 25 to 30 years, people will form relationships. That's not a speculation, that's a certainty. You're taking a small group of human beings, sealing them in a confined space for longer than most marriages last, and expecting them to remain purely professional for 3 decades. That isn't how people work. Relationships will form. Some of them will become intimate, And over 25 years, even with careful contraception protocols, the statistical probability of at least one pregnancy approaches near certainty. Mission planners would have to decide before the ship leaves Earth orbit what to do about that. Here's the thing most people don't realize. We have essentially no data on human reproduction in space. None. No human pregnancy has ever been attempted beyond Earth's gravity well. Animal studies conducted in microgravity suggest potential problems: disrupted bone formation, abnormal organ development, cardiovascular complications in the developing fetus. We know that microgravity affects nearly every biological system in an adult human body. What it does to a developing embryo, we genuinely don't know. A rotating section on the spacecraft could provide artificial gravity, but the rotation rate would need to be calibrated carefully, and the Coriolis effects in a smaller rotating cylinder can cause disorientation even in healthy adults. Whether artificial gravity at the right level would be sufficient for normal fetal development is an open question, a real, unanswered question, not a theoretical one. Now assume everything goes smoothly. The pregnancy proceeds normally, the birth is uncomplicated, and a healthy child arrives somewhere past the asteroid belt, hundreds of millions of miles from Earth. What is that child's world? Think about that for a second. Their entire existence is the ship, the corridors, the hydroponic bays, the observation ports, the hum of the reactor. They have never felt wind. They have never seen a horizon that didn't end at a wall. They have never stood in rain or looked up at a sky full of clouds or walked on any surface that wasn't a metal deck plate. Earth isn't a place to them. It's a concept, a collection of video files and secondhand stories told by people who are slowly forgetting what it actually felt like. Their parents can describe what grass smells like, but the child has no frame of reference for that description. They can't map it onto any sensation they've ever had. By the time that child is a teenager, their psychological architecture would be completely unlike anything we've ever studied in a human being. Their entire social world is the crew, maybe a dozen people, maybe fewer. Every authority figure, every peer relationship, every romantic possibility would exist within that same small group. There's no outside, no other town, no internet full of strangers, no possibility of leaving for college or moving to a new city. The ship is everything. It always has been. It always will be. And here's where this becomes genuinely uncomfortable. That child did not consent to any of it. The adults on the mission made a choice. They understood what they were signing up for. They read the mission briefs. They went through the psychological screening. They accepted the risks with full knowledge of what those risks were. A child born on that ship accepted nothing because they had no opportunity to. They were brought into an environment of extreme isolation, chronic radiation exposure, and no exit by a decision made entirely by other people. Whether that constitutes an ethical violation is a question that doesn't have an easy answer, and reasonable people disagree. Some would argue that life is meaningful wherever it occurs, that a child raised with purpose and care in extraordinary circumstances is still a child with a full life ahead. Others would argue that placing a human being into conditions they never chose, from which they cannot escape, is a form of harm, regardless of the intentions behind it. Mission planners would need to take a position on this before departure. Mandatory contraception for the entire duration of the mission. That's an intrusion on personal autonomy that would be difficult to enforce and legally unprecedented. Voluntary protocols with no enforcement mechanism? That's essentially accepting that births will happen and choosing not to plan for them. Neither answer is clean. What's certain is that if a child were born on that ship, they would grow up as something genuinely new in human history. Not an explorer, not a traveler, a resident. The ship wouldn't be a vehicle they were passing through. It would be their home, their world, their entire context for what existence means. Neptune, to them, would be a destination they were approaching their entire lives. Earth would be a rumor. They would be the first humans ever born beyond the asteroid belt. And Earth would mean about as much to them, viscerally, as ancient Rome means to most people alive today. Let's think about what it would actually look like when things went catastrophically wrong. Not a system glitch, not a bad day, but a real disaster. Because here's the thing, most people don't think about when they imagine a Neptune mission. Every danger that exists in space, radiation, vacuum, micrometeorite debris, biological contamination, equipment failure, exists without any of the safety nets we take for granted. No rescue shuttle, no emergency evacuation, no engineering team on the ground that can get to you in time. When something goes wrong on the International Space Station, there's a Soyuz capsule docked to the side. The crew can be on Earth within hours. At Neptune, the fastest possible rescue mission would take over a decade to arrive. By the time anyone got there, whatever had happened would be long over. So let's start with the scenario that probably keeps mission engineers up at night more than any other. A micrometeorite impact. Not a large one, nothing dramatic or cinematic. Just a particle about the size of a grain of sand. At the velocities involved in interplanetary space, even that tiny mass carries kinetic energy equivalent to a small explosive. The forward shielding is designed to absorb most of these impacts. The spacecraft would have multiple shielding layers for exactly this reason. But shielding isn't perfect. It never is. One particle gets through, punches a hole through the outer hull and into a habitat section, and suddenly the air pressure in that section is dropping. Fast. The airtight doors seal automatically. Anyone in the breached section has somewhere between 30 seconds and a few minutes, depending on the size of the breach and the volume of the space. The rest of the crew watches pressure readings drop on a screen and waits. If the people trapped inside can get to emergency pressure suits in time, they survive. If they can't, or if the suits themselves are compromised, they don't. And that's assuming the breach is in a recoverable location. If the impact hits a critical system, a fuel line, the reactor cooling loop, the water recycling infrastructure, the conversation changes entirely. The repair requires an EVA. Someone has to suit up, go outside the ship in deep space with no atmosphere above them and the full radiation environment of the outer solar system beating down on their suit. The cosmic ray flux this far from any planetary magnetic field is significant. Every hour spent outside adds to a cumulative radiation dose that's already pushing the limits of what the human body can absorb over a lifetime. The crew member doing the repair knows this. They go anyway because the alternative is watching the breach get worse. That's not heroism in an abstract sense. That's a person doing math in real time, trading years of their life expectancy against the immediate survival of everyone on board. Now consider a different kind of emergency, a pathogen outbreak. Before launch, the crew would go through extensive quarantine and medical screening. The spacecraft would be as close to sterile as it could possibly be made. But you can't screen for everything. Viruses mutate. The radiation environment on a Neptune mission is intense enough to accelerate mutation rates in microbial populations. Something dormant and harmless in a crew member's gut microbiome could, under the stress of prolonged spaceflight and radiation bombardment, become something unrecognizable, or something the medical screening missed entirely because it was below detectable threshold at launch. The medical team has limited supplies. Antivirals and antibiotics on board have a finite shelf life, and over a decade of travel, some of those medications will have degraded well below effective concentrations. There's no pharmacy to resupply from. There's no specialist to consult in real time. The ship's physicians are working from whatever knowledge they brought with them and whatever diagnostic equipment they have on hand. In a closed system, a pathogen doesn't run out of hosts. It cycles through the population, mutating as it goes. If it's serious enough, the question stops being about treatment and starts being about containment. And containment on a spacecraft is an almost impossible problem when the air itself is shared. Earth gets the distress message 4.5 hours after it's sent. The reply arrives 4.5 hours after that. 9 hours of round-trip communication time for every exchange, and that's assuming mission control doesn't need time to consult specialists, run simulations, and formulate a response. In a fast-moving medical emergency, 9 hours is an eternity. Then there's the scenario that doesn't announce itself loudly. The reactor anomaly. Not an explosion. Not a catastrophic failure. Just a slow, steady degradation of reactor output. Power generation starts dropping, imperceptibly at first, then measurably, then undeniably. The engineering team runs diagnostics and finds that the reactor core is declining faster than projected models suggested it would. To stabilize it, someone needs to perform a repair that requires working in close proximity to the reactor itself. The radiation exposure involved would almost certainly push whoever does it past any reasonable safety threshold. It might mean accepting a meaningful probability of developing radiation sickness within weeks and aggressive cancers within years. The alternative is doing nothing and watching power output continue to fall until life support systems begin dropping offline. Heating fails first, then atmospheric processing, then water recycling. It doesn't happen all at once. It happens piece by piece over days or weeks, each failure accelerating the next. The crew takes a vote, or the commander makes the call. Someone volunteers, or someone is assigned. The repair happens, or it doesn't. In every one of these scenarios, the decisions are made by people who are years from Earth with no rescue possible, with delayed advice from mission control that may or may not apply to the specific conditions unfolding in front of them. And in the worst versions, the ones where the cascade of failures can't be stopped, where the decisions don't matter because the outcome is already determined, the ship just goes quiet. Decades later, another mission might find them, a silent ship drifting through the outer dark with no one left to explain what happened. Who is in charge on a spacecraft 2.5 billion miles from Earth? When the nearest authority is 9 hours away at the speed of light? It sounds like a philosophical question. It isn't. It's one of the most practical problems the entire mission would face. It's one that no existing legal framework fully addresses. Right now, astronauts on the International Space Station operate under a patchwork of international agreements and national laws, with Earth only a few seconds away by radio. Houston can talk them through a crisis in real time. A chain of command exists. Behind that chain of command is the weight of institutions, governments, and laws that everyone on board recognizes. On a Neptune mission, that structure doesn't disappear, but the enforcement mechanisms behind it essentially do. The commander can give an order. But what happens when someone refuses? On Earth, or even in low orbit, there are options. On a spacecraft 8 or 9 light hours from the nearest courtroom, the options narrow considerably. Here's what makes this different from anything humans have tried before. Naval law comes closest. A ship's captain at sea has historically had extraordinary authority, including the power to confine crew members, restrict duties, In extreme cases under older codes, considerably more than that. Antarctic research stations operate under treaty governance with a station commander who has significant power over day-to-day decisions. Submarines are another comparison: small crews, confined spaces, limited communication with the outside world, a strict hierarchy. These models all have something useful to offer, but they also all share a feature that a Neptune mission wouldn't have: a return date that's measured in months, not decades. A sailor doing 6 months at sea knows there's a port coming. A crew member on a 25-year mission has no such horizon. Think about what that means for discipline. You can confine someone to their quarters for a week. Can you confine them for 3 years? That's not just a loss of individual freedom, it's a loss of a crew member's labor, expertise, potentially their mental stability in an environment where every person matters. The spacecraft might need that person's specific skills. You can't afford to simply remove someone from the working population for years. And yet, if someone becomes violent, delusional, or systematically dangerous to others, you can't simply ask them to step outside. The governance structure would have to be designed before launch with explicit rules about what authority the commander holds, what decisions require crew consensus, how disputes get resolved, what the options are when someone crosses a line that can't be walked back. It would need to be something every crew member signs on to with full understanding of what they're agreeing to. Think of it less like joining a government and more like founding one, a small, closed republic with no immigration, no emigration, no neighboring states to appeal to. The hardest cases are the ones that no set of rules can make easy. What do you do with someone who simply stops cooperating, who retreats, who refuses duties, who doesn't threaten anyone directly but whose absence from the work rotation puts added pressure on everyone else over years? What do you do with someone who becomes a true danger? The extreme scenarios don't have clean answers. They never have. They just usually get resolved by someone with authority calling someone else with more authority, escalating up a chain until something happens. On this mission, you are the top of the chain. There is no escalation path. Whatever decision gets made is the final one. History's isolated communities, castaways, Arctic expeditions, early colonial outposts show that governance failures in closed environments can be as lethal as equipment failures. In some cases, more so. People make it through extraordinary physical hardship. They don't always make it through a collapse of the social order that's supposed to hold them together. And the difference between a crew that holds together for 25 years and one that doesn't may come down to decisions made in a conference room on Earth, years before launch by people who will never be on the ship. You'd need a legal and governance framework that the crew agrees to before launch. This was because once you're underway, there is no external authority, no appeals process, no one coming to help you sort it out. So after all of that, the radiation, the isolation, the 2 decades in recycled air, the near certainty of a one-way ticket, you might reasonably wonder who on Earth would actually say yes. The honest answer is that some people would, not many, but some. And understanding who they are and why they do it tells you something important about what kind of mission this would actually be. Start with the simplest motivation: the adventure. To be the first human being to see Neptune with your own eyes, not through a telescope, not through images taken by a robotic probe 35 years ago. With your actual eyes, through an actual viewport, close enough that the planet fills the frame. For a certain kind of person, that experience alone is worth almost any price. History is full of people who walked into unknown territory knowing they might not walk back out. Some of them were driven by duty or desperation, But some of them went simply because the unknown was there, and they couldn't bear not to see it. Those people exist today. They're in astronaut programs, in military special operations, in remote scientific outposts in places that most people would find unbearable. For them, the cost of not going would feel higher than the cost of going. Then there's the science. Here's the thing most people don't realize about Neptune. We know almost nothing about it. Everything we have comes from a few hours of flyby data from Voyager 2. One pass, no orbital observations, no follow-up missions, no ground truth. A crewed mission that could spend months or years in the Neptune system would transform our understanding of ice giant planets, of the early solar system's formation, of how Neptune generates its own internal heat, of what Triton's subsurface looks like, of whether those geysers indicate something warmer and more complex beneath the surface. For a scientist with a genuine obsession, and the people who end up at the frontier of planetary science tend to have exactly that, the idea of being the person who finally answers those questions could outweigh almost everything else on the ledger. Then there's legacy. Think about what it means to have your name attached to this. The first humans to reach the outer solar system. The people who actually went. That's not a footnote. That's the first line of the chapter. As long as human civilization exists and keeps records, those names survive. Some people are motivated by that. Not in a shallow way, but in a genuinely considered way. They've thought about what a human life amounts to and decided that doing something unprecedented, something that will matter to the long chain of people who come after, is worth a great deal of personal cost. Some would go for reasons that are harder to explain, a desire to start completely over, to leave behind a world that felt too small, too complicated, too full of things that couldn't be fixed. The spacecraft becomes a kind of answer to a feeling that Earth never quite resolved. That's not a pathology, it's a recognizable human impulse. The people who crossed oceans in wooden ships weren't all fleeing something terrible. Some of them just needed to go somewhere that no one had been, and the need was strong enough to override everything else. And then there's the long game argument, the one that says humanity's survival requires expansion, and expansion requires someone to go first. The people who believe this really believe it, not as an abstraction but as a practical conviction, would see a Neptune mission not as a sacrifice, but as an investment. They'd be paying a price that future generations wouldn't have to, and they'd consider that a reasonable trade. So who are these people specifically? They're not reckless. That's worth saying clearly. Reckless people don't survive the selection process, and they don't function well in the kind of environment we've been describing. The crew of a Neptune mission would be among the most carefully evaluated human beings ever assembled. Years of psychological screening, thousands of hours of training across multiple disciplines, medicine, engineering, biology, navigation, systems repair, the capacity to remain cooperative and effective under conditions of extreme stress and confinement, and a clear-eyed acceptance of the probability that they were not coming home. They would know. That's not something the mission planners would obscure or soften. The math would be presented to them honestly, and they would sign on anyway. Not out of ignorance, and not out of recklessness. And some would go for reasons they couldn't fully articulate even to themselves, something older and less logical than any of the practical motivations, something that sounds almost like a compulsion. Let's step back from the individual experience and think about what a crewed Neptune mission would actually mean in the larger story of what we are. The Apollo missions took humans to the moon, roughly 240,000 miles from Earth. That number already felt impossible when Kennedy said it out loud in 1962. Neptune sits 2.8 billion miles from the Sun, a crewed mission to Neptune would be, by any honest measure, more than 60 times farther than any human being has ever traveled. That's not an incremental step. That's a different category of achievement entirely. Here's what that distance means in human terms. Every mission we've ever flown, every spacewalk, every lunar landing, every orbital station has existed within what you might call the neighborhood. Close enough that rescue was at least conceivable. Close enough that Earth was a living, visible presence in the window. The crew of a Neptune mission would leave that neighborhood permanently. Earth would shrink to a pale dot. Then it would vanish from the naked eye entirely. They would be operating in a regime of isolation that no prior mission has ever touched, doing it for decades, and doing it with the full knowledge that the planet they came from was simply too far away to matter in any practical sense. And yet, that's exactly what makes it meaningful. There's a long arc here that's worth tracing. Our ancestors pushed canoes into open water with no charts and no certainty of what lay beyond the horizon. Polynesian navigators crossed thousands of miles of open Pacific using stars and wave patterns and an accumulated knowledge that was passed down through generations of people who were willing to go first. European sailors crossed the Atlantic with ships that we would now consider barely seaworthy, into weather systems they couldn't predict, toward continents they had no real knowledge of. Some of those voyages were one way by circumstance. Ships wrecked, crews died, but the knowledge they brought back, and sometimes the colonies they established, changed the trajectory of human civilization. Every map that exists today has those voyages written into it somewhere. A crewed Neptune mission would do the same thing at a scale those navigators couldn't have imagined. It would prove something about what humans are capable of sustaining, not just physically, not just technologically, but as a civilization. It would mean we built a machine that kept people alive for 25 years without resupply. It would mean we solved life support at a level nobody has ever solved it. It would mean we selected, trained, and sustained a crew through conditions that no psychological study has ever fully modeled. Every one of those accomplishments would be foundational, not just for future Neptune missions, but for everything beyond. Because Neptune isn't the end of the solar system, it's closer to the beginning of the outer solar system than it is to anything that lies beyond it. The Kuiper Belt extends past Neptune for billions of additional miles. The Oort cloud, the vast shell of comets and ice that represents the true outer boundary of the Sun's gravitational influence, stretches out to perhaps 100,000 astronomical units. Neptune is the first step into a region of the solar system we have almost no experience with. The crew who reaches it would be standing at a threshold, not a destination. There's a philosophical dimension to this that's hard to overstate. From Neptune, the sun is not a warm, generous star. It's a bright point of light in a crowded sky. It provides almost no heat and almost no navigational warmth. Earth is invisible. The entire inner solar system, everything humans have ever called home, is compressed into a tiny region of sky that you could cover with your thumbnail held at arm's length. The crew would look back and understand, viscerally and immediately, what it means to be truly distant from everything they knew. That perspective doesn't leave you unchanged, and it wouldn't leave humanity unchanged either. Every civilization that has ever expanded its reach has been fundamentally altered by the expansion, not just by the resources or the territory, but by what it learned about itself in the process of going. The first humans to reach Neptune wouldn't just be travelers, they'd be the opening sentence of a chapter in human history that we haven't written yet. We've always pushed past what seemed possible, and whatever drives that, curiosity, ambition, something instinctive and hard to name, It's the exact same thing that would one day put someone on a ship pointed at Neptune and watch them go. Tonight, we've looked at what it would truly take to reach Neptune. The distances, the propulsion challenges, the life support requirements, the radiation, the isolation, the physical and psychological toll, and the near certainty that anyone who made the journey would never see Earth again. And here's the thing that's hard to sit with. None of what we've covered tonight is speculation. The rocket equation is real. The radiation environment is real. The communication delays, the biological deterioration, the psychological weight of decades in a closed metal system with no exit. All of it is grounded in physics and biology and engineering that we already understand. We're not describing a fictional dystopia. We're describing the honest consequences of what the solar system actually looks like at its edges. The distance alone would sentence any crew to a life defined entirely by the mission. No fresh air, no open sky, no one outside that ship who could help them. The sun would shrink to a bright point of light. Earth would eventually disappear from sight entirely, and the people who went would know before they left that this was probably how it ended, not with a dramatic failure, but with the quiet arithmetic of fuel mass and travel time and accumulated radiation slowly making return impossible. So why does any of this matter? Why spend this much time with the mission that hasn't happened, using technology that doesn't exist yet, facing obstacles that might not be solvable in our lifetimes? Because it's coming. Maybe not in 20 years, maybe not in 50. But the direction of human history is not toward staying put. Every ocean that looked uncrossable eventually had ships on it. Every summit that looked unreachable eventually had footprints on it. Neptune is the next version of that, the edge of what is known, sitting 2.8 billion miles away in the dark, waiting. The people who will eventually go are probably alive right now. They're young. They don't know yet what they'll do with their lives. But somewhere in the future, they'll sit in a briefing room and look at the numbers and understand exactly what they're agreeing to. And they'll sign anyway. Not because they don't understand the risk, because they do. If you've made it this far and you find yourself captivated by what lies beyond Earth the way we are, take a moment to like the video or subscribe to the channel. It genuinely helps us keep making content like this, and it means more people get to have this conversation. Go outside tonight if you can. Look up. Neptune isn't visible to the naked eye. It's too far, too dim, a pale blue point even through a decent telescope. But it's there. 2.8 billion miles of cold silence between you and a world of storms that moves faster than any wind on Earth, circled by a frozen moon shooting nitrogen into the void. Sleep well tonight, knowing that out there, 2.8 billion miles away, is a blue world of storms and ice and nitrogen geysers that no human eye has ever seen up close, and that someday, somehow, one of us is going to go.